So now we're going to go into ensembles where we're going to take multiple supervised models and combine them together into, for lack of better words, one supermodel. So one application of ensembles that was used was with Netflix when they wanted to improve their movie recommendation system. And so what they did was they needed a large amount of data on their movie ratings, so they collected them from their users by creating a contest. And one of the things that they found was that groups of people started kind of voting together. And when they started working together and started combining, those ensemble predictions ended up being a lot more accurate than any of the individual predictions that were made. So with ensemble learning, so far our learning methods that learn a single hypothesis from a chosen hypothesis space that's used to make our predictions. Now with ensemble learning, we can select a collection or sample, an ensemble of hypotheses and combine their predictions. So our first example is we could generate 100 different decision trees from the same or different training set and then have them vote on the best classification method for a new example. The key motivation on ensembling is to reduce your error rate and hope that it'll become much more unlikely that the ensemble will misclassify an example. So ensemble learning is a technique that creates multiple models and combines them to produce improved results. So ensemble learning will usually produce more accurate solutions than a single solution, like we saw with the Netflix example. There are two steps to ensemble learning. First, the machine learning. We're going to have multiple machine learning models that are created using the same or different learning algorithms. And these are going to be called our base models. And then we have predictions formed on the basis of those base models. So the value with ensembles is kind of goes back to this no free lunch theorem, saying that there's no one algorithm that's just going to be perfect in all situations. And so when we're able to combine our algorithms together, we're able to cancel out some of that random error and allow for our correct decisions to be reinforced and if not amplified. So ensembling is useful not just for prediction of cross-sectional data, but it's also helpful in time series forecasting. And so we can kind of look at weather patterns as an example of an application of this. So, why can ensembles improve our predictive accuracy? So, the principle of combining methods is going to be popular because it reduces risk. So, it's the same concept that's being used when you have a finance portfolio and you create that to use a combination of stocks to combine to make your portfolio. That's going to allow for you to kind of reduce your risk because the return from the portfolio is typically going to be less risky than the variation of the individual stocks. And so that should be smaller than the risk of our individual components. And so when we're talking about risk and predictive modeling, this is going to be the equivalent to the variation in prediction. And the key is to reduce the variance in our predictions. So, suppose that each model produces prediction errors that are on average 0. And so if our prediction methods are unbiased, we can take the average of two predictors and the expected mean will be 0. So therefore the ensemble will have the same mean error as the individual models. The variance of the prediction errors can be lower than each of the individual variances in some cases. And the key is going to be to look at those covariances between the two prediction errors. And the variance of the average prediction error will be even smaller than each of the individual variances. And it gets even smaller still if the prediction errors are going to be negatively correlated. So if I have a homogeneous ensemble, that basically means that I'm using the same learner over and over again on different data sets. And so There are a couple different things that we can do when we're training our data. We can do some simple averaging, and we'll look at that in here a little bit. We can use bagging, or we can also use boosting. So we have different learning algorithms and algorithms with different choice of parameters. The data set with different features, so maybe a different random subspace. We have different ways of collecting our data set, so whether or not we're using bagging, boosting, averaging, or so forth. Right, so ensemble methods are going to be applied to regression as well as classification. If we're looking at regression problems, we could create multiple repressors, which are basically multiple regression models, such as linear or polynomial or whatever. And if we're working with our classifiers, it can create multiple classifiers as well. And so that would be, multiple classification models like KNN, logistic regression, decision trees, and so on. And so when we are looking at our different types of ensemble learning, once again, we have bagging, boosting, we have decorate, and we also have random subspace or random forest. So most of these might be fairly familiar to you right now, but we're going to talk about them anyways, regardless of your level of familiarity. So with simple averaging, when you have a numerical outcome variable, you can choose to use the average of the predicted values, or you can use the median value for prediction. One of the benefits of using the median of the predicted values is going to allow for you to your model to be more robust to extreme prediction values. Another option would be weighting averages. Those can be useful as well. You can set the weights proportional to the quantity of interest, so maybe setting it proportional to the accuracy of the model or even the amount of data. If your data are categorical, you're looking at classifiers, so that's going to work through voting. Classifiers are going to be combined in a static way. Each base level classifier is going to give a weighted vote for its prediction. We have what's called a plurality vote, so basically each base classifier is going to predict a case. And then your class distribution vote, so each is going to predict a probability distribution, and that's given here on the screen for you. Another way to continue combining our ensemble of classifiers, you can do stacking, you can do cascading. Stacking allows for you to do it dynamically, and so you can use machine learning to learn how to combine the prediction of the base level classifiers, and then your top level classifier is going to be used to obtain that final prediction. With cascading, it's going to combine your classifiers iteratively, so one at a time. And after each iteration, you end up with your training data set being extended to include the predictions from the previous iteration. So let's look at bagging. Bagging is going to be where you take M samples of N data, so however many samples you have of whatever sample size with replacement. And so you're going to build a classifier on each bootstrap sample, and you have a probability of getting 1 minus 1 over N raised to the N of being selected, and that same probability is the proportion of the data that gets selected to make your training data set. So this is called the 0.632 bootstrap because since any particular training data has a probability of being selected of 1 minus 1 over n of not being picked, that means it's got a probability of not being selected n times of 0.368. And so this ends up meaning that the training data will contain approximately 63.2% of your instances. And so with bagging, that's bootstrap aggregation. That's going to repeatedly randomly resample your training data. And you're going to draw however many in observations X times with replacement. And those are called bootstrap samples. And on average, like I said, they're going to contain about 63.2% of unique training examples. And the rest are going to end up being replicates. And so when you're working with bagging, you're going to combine your outputs by voting. And this is going to end up decreasing your error because it's decreasing your error, your variance in your results due to maybe unstable learners earlier on in your process. So examples of unstable learners might be decision trees or maybe neural networks. And so those outputs can change dramatically if we change our training data slightly. So when we start using bagging, that allows for that to kind of even out a little bit. So continuing on with this, we're going to get a standard training set of D size whatever n, right? So for I being 1 all the way up to m, which is however big you need it to be, you're going to draw a sample size from D uniformly with replacement, and you're going to make a classifier. And your final classifiers are going to be a vote of all of your classifiers combined together. And so if I were looking at an example here, I'm trying to find a collection of 10 simple thresholding classifiers that collectively classify correctly. And so here we have every classifier learns a threshold such that if x is less than t, then we've got our classifier. If not, it's not going to be it. And so here we can see kind of what our training data set would look like on the x-axis. And on the next slide, we're going to look at a bunch of different iterations, and you can see the different rounds that were made, starting with round 2 for bagging, looking at the different rules that were used. And so if we have bagging applied to our data, here we have an example of combining classifiers being constructed using that bagging approach. And remember, once again, the really cool thing about this classifier is that we end up with 100% accuracy. If we have n simple classifiers, they're going to work like a complex classifier. So depending on however many we have, we add them all up, that they kind of work together like a big classifier together. Just remember your initial data would not be correctly separated by a simple classifier, but when they work together, we're able to get that perfect classifier, which is really kind of cool. With bagging, remember, bagging's going to work well if our classifiers are unstable. In fact, it complements each other pretty well. So if we're using like decision trees or neural networks, those are going to be they're going to do really well with bagging. We end up with the increased accuracy because we're reducing our variance in our individual classifiers. And because of this, it's not going to be focusing on any particular instance of the training data, which makes it less susceptible to overfitting. So what if we want to focus on a particular set of instances in our training data? So when we go to boosting. So remember, boosting is an iterative procedure to adaptively change the distribution of our training data by focusing more on your previously misclassified records. So initially you have all n records are assigned to equal weights, but unlike bagging, your weights may change at the end of your boosting round. And the higher the weight of a record is going to increase its probability of being selected the next round. So if we were to look at this example here, we have our original round data. We keep trying to predict it, and we see here that example 4 was really hard to classify, and its weight just ended up getting increased, resulting in it being more likely to be chosen by the time we got to round 3. So when you construct a weak classifier, you're going to use a different data distribution. You can start with uniform weighing, and then during each step, you can increase your weights of your examples or decrease your weights depending on whether or not they were correctly or not correctly learned. And the big idea is that you're going to focus on difficult examples which are not correctly identified in previous steps so that you can make your model better. And so the intuitive justification is that models should be experts that complement each other. So this goes back to that discussion of modeling our errors and the errors of our errors. So when we combine our weak classifiers, we have weighted voting, which means we're going to construct a strong classifier by weighted our voting of the weak classifiers. And the idea behind it is the more votes I have, the better it's going to get. And so if I'm going to iteratively add my weak classifiers, this is going to end up allowing for me to increase the accuracy of the combined classifier through minimization of that cost function. So let's think about adaptive uh, boosting as if we have every rectangle in this picture over here is has the weight proportionate to the height. Okay, and so I have my next chance where you see that my first section is wrong. These ones that are right, they got to be bigger. And so as we keep going forward, we can kind of see how the crosses are going to correspond to our misclassified examples, and the size of the tree is going to indicate that the weight of that hypothesis in that final ensemble. There's an add a boost pseudocode that you can kind of work through to think about kind of how it works. And so I thought this process was kind of interesting to look at. We have an illustration where we have our original data and we put some initial weights on each data point, and we take the points out for training, and then we do boosting. So here we see classifier 1 was wrong on these two samples, so their weight ended up getting boosted up, and it ended up being increased. And so we can look at boosting from round 1 to round 2 to round 3 to kind of see how overall we magnified our errors so that we can correctly classify them later. So when we're looking at weighted examples, we have a generic approach where we replicate our examples in the training set proportional to their weights. Um, One thing to keep in mind is that most algorithms can be enhanced to effectively incorporate the weights directly into their learning algorithm. When we're looking at decision trees, we can calculate information gain. When counting, for example, we have our simple increment of corresponding our count by W rather than by 1. And you can apply boosting without weights. So remember, you're just resampling with probability determined by your weights. I mean, the disadvantage to this is that not all of your instances end up getting used. But an advantage is if your error is greater than 0.5, you can resample again. So here we're looking at some restaurant data, and a decision stump is going to be a decision tree with just one test at that root. And so here we see the relationship between the proportion correct on the test set compared to our training set size. Our boosted decision stumps are doing much better overall than our decision stumps. And then if we look at it again, we see that our training error is going to reach 0 when our size is 20, which is predicted by the theorem, and it's going to remain at 0 as more stumps are added to our ensemble. So ensembles, based on some experimental results, they've been used to improve the generalization accuracy on several problems. On average, boosting is going to provide a larger increase in your accuracy than bagging. But on rare occasions, it can degrade your accuracy. Bagging is more consistent in providing modest improvement. Boosting is very subject to overfitting your data when you have a lot of noise in your training data set. And bagging is easily parallelized, and boosting is not. So, real brief overview or reminder of Forest. This is an ensemble method specifically designed for our classification trees or for decision trees. And you can grow a whole bunch of trees with this, and you can have a whole bunch of unpruned trees. And each base classifier is going to be a new vector of attributes from the original data set. And then your final result on the classifying a new instance would be based on voting. And so your forests choose the classification result that have the most votes. We now have two new sources of randomness. So we have bagging and random input vectors. Our bagging method, that randomness comes because each tree is grown using a bootstrap bootstrap sample of training data. And then our random vector methods, at each node, the best split is chosen from a random sample of however many attributes we're looking at instead of looking at all of our attributes. So when we're looking at the random forest algorithm, we need to let the number of training cases be whatever value, and then the number of classifiers of our variables be m. And then we're told the number of classifiers of input variables to be used to determine the decision at the node of our tree. And remember, this should be much less than our number of classifiers. Then you choose a training set for the tree by choosing n times with replacement from all of our available cases. And so remember to take a bootstrap sample. That would be a good choice at that point. And then you use the rest of the cases to estimate the error of the tree by predicting their classes. And each node of the tree randomly chooses a certain number of variables on which to base the decision at the node. And then you calculate the best split on these variables in our training set. And then each tree is going to be fully grown without being pruned, as it might have been done using some other methods with trees. So if we look at a schematic of what's going on with our random forest, we start with our original data, we do a little bit of randomization, we build a whole bunch of trees, and then the results of that get averaged together. We have the decorate, which comes from Melville and Mooney. So we're going to change training data by adding new artificial training examples that encourage our diversity in our ensemble. And this helps us to improve our accuracy when our training set is really small. And so because when we resample and reweight the training set, we would have limited ability to generate diverse alternative hypotheses. So what this looks like is we start with our training examples, our artificial examples, and our base learner is going to take some observations from our training sample and put it into my current ensemble. Okay, and that's going to be classifier 1. Now, that classifier 1 is going to go and inform what's going to happen with our artificial examples. Now, from my artificial examples and my training examples, my base learner is now going to take observations and prepare classifier number 2, which then goes back and informs what happens with our artificial examples. And then our base learner pulls more data to make our classifier number 3. So when we're thinking about ensembles and active learning, ensembles are really good to actively select good new training examples. You're going to select the unlabeled example that causes the most disagreement among your members of the ensemble. So some different methods that we have query by bagging, query by boosting, and active decorate. Let's look at active decorate. So we've got our training examples going through decorate into our classifiers, and then we take our unlabeled examples and we use those classifiers to label them. And so we have different unity values depending on how they behave, and then we can acquire a label and then send that back to our training examples. So we also have the meta decision trees, so that's a type of stacking. It uses a little bit different algorithm for your different base level classifiers. This is going to be a decision tree whose leaf leads to a prediction of which the base level classifiers could be used. And so MDT level attributes are going to be something that can be calculated from the prediction of the base level classifier. Or they can also just be a set of base level attributes. And so these decision trees are going to be really helpful when your data are going to be coming from heterogeneous subdomains. Stacking is also known as stack generalization, but basically you're going to take multiple machine learning models, combining them together to make a machine learning algorithm. And the basic idea is that you're going to train this algorithm with a training data set and then generate a new data set with these models. And then these new data set is going to be used as an input for the combiner machine learning algorithm. So we have optimal decision trees versus meta decision trees. Here we can see that optimal decision trees use class values predicted by the base level classifiers as attributes. And our meta decision trees don't do that. And then our optimal decision trees will predict the class value in its leaf nodes, while we don't see that in our meta decision trees. So we have some advantages and disadvantages of ensembling. I mean, an advantage is that it's more precise predictions, it helps improve stability, helps to avoid overfitting. But some disadvantages, it takes more resources like so your computer processing. It takes time while you wait for it to process, as well as to collect enough information to do that. And then ensembles are really not that easily interpreted. They're pretty much called black box models.